Okay, this is section 4 of chapter 3, and it is about concavity and points of inflection and the second derivative test. So first of all, concavity, what is it? It is the shape of a graph the shape that the graph makes related to slope. And so when you look at, there's two forms of concavity: concave up, concave down. When we look at concave up, when we're increasing x to the right, the slope is increasing. Although it is negative as it starts out, it's constantly getting more positive, constantly increasing. So the derivative is constantly increasing. And we'll learn about this bottom half in a second. And then when we look at concave down, as the x increases to the right, the slope is constantly decreasing. The derivative is constantly getting less positive, more negative. So as we look at it in a together form, we see that the slope decreases, but then there's this point that the slope begins to increase. And that is called the point of inflection. It is at the point that the second derivative, which we're going to learn about, changes sign, and that is the rate of change switches so that it flips. It goes from positive to negative, and you never want the second derivative to equal to 0 because then it's undefined, and then you have to use the first derivative in order to figure out what the maximum or minimum of the shape looks like. But the second derivative always has to switch signs at a point of inflection, and that's where the slope switches from decreasing to increasing, or increasing to decreasing. And then we have the second derivative test. This is what it is. It's pretty much, if the second derivative is greater than 0, then it's a minimum on the graph. If it's less than 0, it's a maximum. And the way we use it is we find the critical points from the first derivative, and then we find the second derivative and plug those critical points into the second derivative. And if it whatever it is, one of these two, but if it equals 0, then it's undefined, and we have to go back to just using the first derivative. And the more derivatives, the more specific you get. So let's look at number 2. Number 2 is just asking us to determine on which the open interval is looking. And when we remember that concave up, and then there's concave down, and concave up is shaped like a cup, that helps, and concave down is a frown. So looking at it like that, we can see that it begins to be a cup at the very beginning, and then it turns to a frown. And at the point that it turns to a frown is 1. So from that we can learn that the intervals are from negative infinity to 1 it is concave up, it's a cup. And then from 1 to infinity is concave down, and at 1 is a point of inflection. Okay. Number 8 is also similar. Yeah, I didn't show the graph, but I just graphed it because I want you to get to understand what we're looking for when we want concave up and concave down. And in this one, it starts out as concave down, a frown, and it comes from negative infinity to 0. And we're looking at the x, and then at 0, it switches from its point of inflection, and then it goes from concave down to up, and 0 to infinity is concave up. And that's all that they ask you. Yeah, so okay, so 14. What we're trying to do is we're trying to find the point of inflections and then talk about the concavity. So we find point of inflections by finding the second derivative, finding the zeros, and then picking values on each side to make sure that that it's actual sign switching. So we find both of them because we're also going to have to talk about the concavity. So here's the second derivative. We set it to 0. We get x equals 0. So that's a supposed point of inflection, x equals 0. So we put values on each side to see if it switches sign, but it doesn't. Negative 1 also gives us 24, and 1 gives us 24. So it's not a point of inflection. I don't know what it is, but it's not a point of inflection. So we have to go through a different way to figure out, well, there's no point of inflections, first of all, but then we have to go through a different way of figuring out concavity. So we go back to the first derivative, and we figure out the zeros, and we figure out that the critical point is x equals 1. Now a great way to figure out, because we already learned kind of a cheat sheet, that if we just take the critical points and plug them into the second derivative, we can figure out what it's telling us, and we can tell us if it's a minimum or maximum, and that therefore tells us the concavity. If it's a minimum, it's a concave up. If it's a concave down, it's a maximum. So we plug 1 into the second derivative, and we came with a positive number, which means it's greater than 0, and it's a minimum, so it's concave up. So 29. So they're again asking us to find all relative extrema and use the second derivative test where applicable. So we don't know the shape of this function at all. So we first figure out the first and second derivative. Second derivative is only a constant, which right away tells us that it's not a point of inflection. It's constant, nothing's changing, so there's no worry there. But that means we have to figure out a different way to find minimum or maximum. However, the one thing the second derivative does tell us, because it's greater than 0, is that it's a minimum right away. So that tells us that this entire thing is just one minimum. So there's no interesting thing going on besides that. I didn't finish my concave up. And that therefore tells us that it's all concave up. It's all shaped like a cup. And then we can just plug in the critical point that we find, and we can find at what point it's the absolute minimum, and so it's at 5, 0 that it's a minimum. 35. So 35 is doing the exact same thing. So we're taking and finding both the first and second derivative, and then we can find the critical points, and we find that the critical point is x equals 0 by taking the first derivative, setting it to 0. But when we put x equals 0 into the second derivative to find our to evaluate whether the concavity in the shape, we get undefined. What does that mean? We don't know. So we have to just go back to using the first derivative. So we put values on both sides of the function, both sides of 0, both sides of the critical point into the second derivative, and we get the first negative one gives us a negative. So on the left it's negative, and on the right it is positive 2/3. So that tells us that it goes from positive or negative to positive, which is a minimum. So this entire thing is just one big minimum, and the minimum, absolute minimum, is at 0, comma, -3. So that is concavity and the second derivative, and also points of inflection. So hope that helped.